Hi, so let's finish here with last two sections in Chapter 12 that you're responsible for. 12.5, really all it is an introduction to two special bases. And these are special because it happens to be what your calculator will do for you. So if you've had a calculator and you've been trying to use it to solve questions that came up before, you are probably not very successful most of the time because our calculators only do base E and base 10, this common log and natural log. Okay, so a common log, when we say common log, it is base 10. Okay, and something else to keep in mind, if it's a common log, if its base is 10, then we don't have to write the base. So it's kind of like a square root. If you have a radical and there isn't a special index given, it's understood to be 2. Right? So the same thing with the logarithm. If there's not a specific base written, it's understood to be 10. So log of x is the same thing as log base 10 of x, right? Just like radical x is the same thing as if I write the radical, and I put a little 2 in there. Right? So if it doesn't have a base written for your logarithm, it's a 10. And that's called the common log. And on your calculator, that's the button LOG. Okay, that's what the calculator button looks like. Now the natural log is log base E. Okay, now I'm not sure if you know what the number E is. Have you guys ever heard that? Right, so it's kind of like pi. E is an irrational number, meaning that it can't be written right as a terminating decimal. It's one of those numbers that goes on forever and always, kind of like pi. Right, so if you thought pi was the number 3.14, well, it goes a little bit farther than that. Okay, hold on, I'm going to try the exposure here, see if I can get a better image to show up. Maybe a little bit better. Okay, so E is about that number, right? Pi is 3.14159, maybe? Something like that. E is 2.71828. I can't think of what comes after, but it goes on and on and on. Okay. The symbol for log base E is this, ln. That's how it looks on your calculator. So that button that had the capital L and capital N that you were wondering about, it's the natural log. Okay. So log base E of x can be written as ln of x. So that time I wrote them both lowercase. It really doesn't matter. Just make sure if you write it lowercase that your L doesn't try to be a 1. Okay, so if I see ln of x, natural log of x, that's the same thing as log base E of x. So let's go ahead and grab your calculators if you haven't already. And let's find out what these values are on our calculator. Okay, so I'm going to see, I have a TI-30 here. So notice I'm putting squiggle lines, squiggle equal lines. Do you know what that means? Yeah, we're approximating. At some point we're going to stop writing decimals, so it's approximately the same as. Okay, so log, can you find the log button on here? LOG. Right, so mine's over on the left-hand side, just below the second button. Okay, so, and I'm not sure of the order of operations here. I'm just going to try. So I'm going to do log. Oh, and notice it starts with a parenthesis. I know that's really hard to see. Okay, now I'll take the white paper off, see if that helps. It has all these features on it. Oh, it got pretty dark. If I put in the number 5 and close my parentheses and hit enter, I have 0.69897. Did you guys get that? And then there's other stuff, but I'll stop writing there. 69897. I am sure MyMathLab will give you a rounding position. So round to thousandths or something. I just typically round where it feels nice. Okay, so that's all there is. If we're using our calculators to approximate, we're just punching it in. So log of 300. Oh, I hit it too soon, sorry. Log of 300. And you actually don't need to close off your parentheses, so I won't. So 2.477. Okay, good. Now, before I go do the next column, let's think about, does this make sense? So let's see if we can build in some numeracy, some numerical sense. Does this seem reasonable? So remember we'll do this one down here. Your base is 10. And remember what a logarithm does. It's like, what would the power of this number be? What would I have to raise the number 10 up to get 300 out? Right? Well, we found the answer. It was 2.477 with a bunch of other stuff there. Okay. Well, think about, what does 10 squared equal? Right? 200. And what does 10 cubed equal? Right? 1,000. Well, since 300 falls between these two, we would expect our logarithm to fall between the 2 and the 3, which it does. And it's not linear, so if you were thinking, right, it's tempting. It's like, oh, well, your 300 is a whole lot closer to 200, so I think it should be 2.1 or 2.2, something smaller. It's kind of halfway in between, isn't it? So think about your logarithm graph, right? A general logarithm graph looks like that. So it's not a straight line. Okay, so now let's practice. I'm going to cover that up so I can do the other side of my page. And that's finding natural log. So the natural log is the button right below, so ln. So natural log of 5. It's a little bit bigger, right? I have to raise the number 2.718 to a bigger number to get 5 out. It seems to round nicely at hundredths. 1.61. A natural log of 300. 5.704. Okay. You have to pick a place to round, and I was just kind of randomly looking. Okay, great. So that's so we know how to do them on our calculators. Now, let's talk about the graphs. Hey, you know what? I'm not going to see a whole lot of difference in my graphs, so I'm going to graph. Right, I still have my asymptote. Of the y-axis. And I still have my x-intercept of 1, 0. Okay. And the natural log of x, my graph is going to look exactly the same as that one. So if I graphed them on a graphing calculator, they'd look slightly different, but really, if I'm just sketching, it's going to look the same. Okay. If I've got a chance, I'll go ahead and bring my graphing calculator up here, and I'll show you how they look different. So here, let's put a couple of Chapter 12 sections together. So let's sketch f of x equals log, what's the base? 10 of x over 100. Okay, so I have my basic shape of a log graph. But my argument here is a quotient. And how do we rewrite if I have a quotient? Right? It's the log of the top minus the log of the bottom. Great. But what's the log of 100? What's log base 10 of 100? And it's totally fine if you want to stick that 10 there because it feels better, keeps you on track, that's perfectly fine. Right. Well, now I have my log base 10 of x graph minus 2. So from way back in chapter 7, no, maybe chapter 11, when we were moving our quadratic functions, same idea. I'm going to take my basic shape and move it down 2. Now I don't have very many points on my graph. In fact, I only have one. So that's the only one I'm going to move. I'm going to grab that point that used to be here at 1, 0 and move it down 2 and then draw the same general shape. All right, so there's my down 2. Still have my asymptote, still growing slowly. So the thing about logarithmic graphs is they grow really fast at the start and then they taper off. They're always growing a little bit, but it gets super slow. Okay. So think there is a change of base formula, and this is very handy because of what our calculators will and won't do. Okay, so if I have the log base b of m, this is equal to the log base 10 of m divided by the log base 10 of b. Okay, or the natural log of m divided by the natural log of b. So it lets our calculators help us with logs that we can't just figure out. Okay, so let's take a look here. Log base 3 of 15. So I don't know. I know you're tempted, if it was multiple choice, I promise you 5 would be a guess, right? Would be one of the choices. But it's the exponent we're looking for. What do I have to raise 3 to get 15 out? So let's ballpark it. So what's 3 squared? 9. And what's 3 cubed? 27, right? Okay, so since 15 falls in this, right between those two, I'll expect my logarithm to be between those two, between 2 and 3. Okay, so just so we have an idea. So now, the way we do it is you have to pick either common or natural log, doesn't matter. But I'll do log of the argument, so log of 15 divided by the log of 3. Okay. And then let's see what that is approximately. So I'll move this. Let me see if I can get it to show up nicely. Take my white paper off, bump up my balance. Okay, so here we go. I'm going to do the log of 15. Now notice my calculator started with a parentheses. Did yours do that too? Okay, so that means we have to close the parentheses before I do my next logarithm. So close off those. I typed a 0 by accident, so I just arrowed over and I'll get on top and divide. And now log of the base, which was 3. 2.46, awesome, right in between like we were expecting. 2.46. So if you would like, you can go ahead and grab your calculator and show that you get the same result if you would have done natural logs of 15 and natural log of 3, right? You'll get that same decimal approximation. Okay, how about this one? Go ahead and try it. Hit pause if you want, and then come back. Log of the argument over log of the base. Oh, negative. Interesting. Negative 1.585. Everybody get that? If you didn't, make sure you closed off your natural log of 1/3 and then do your division and then natural log of 2. Okay. If you did common logs, that should be fine. You should get the same number out. Okay. Just a quick note on inverse functions. Remember how we talked about it before? In 12.1, we found our inverse functions, and then we did a composition. Okay. Well, e to the x and natural log x, these are inverses of each other. They undo each other. This is super important for later. Okay, so I don't know what that line there was supposed to be. So let's graph f of x, e to the x. Do you remember what that looked like? Right, starts low, goes high. Oh, I only brought one color in today. Sorry about that. Okay, so here's f of x, e to the x. What's the domain? Right, all real numbers. What's the range? What y values do we get out? Yep, 0 to infinity. And what kind of intercept do we have? Right, we have a y-intercept of 0, 1. So if you don't remember that, go back to the exponential chapter and look at how we graphed exponential functions. Okay, x-intercept, your answer would be, where does it cross the x-axis? Right, it doesn't. So that's all of our e to the x information. So now let's look at, oh, there we go, I'll fix it. G of x equals log base e of x. Right? The other way we can write natural log of x. So just look at your other page. It's graphed on the other side. Okay, that has your asymptote here and comes out. So this is our g of x, natural log of x. What's the domain? What x values can we use? Right, 0 to infinity. We only do the logs of positive things. Range, what y values do we get out? Negative infinity to infinity. Good. And then what about the intercepts? So this time I don't have a y-intercept, but the x-intercept, I do have one, right? And it's 1, 0. So think back to 12.1 and how we found inverse functions, right? And what all happened, right? The domain and range switch places. So all real numbers for the domain, all real numbers for the range. 0 to infinity for the range, 0 to infinity for the domain. Okay, so all of that makes sense. And these two are reflected over that line. What's that line I just drew in? Right, y equals x. Okay. Now, one more thing before I let you go, before I get on to my next section, because this influences our next section. What did we know if two functions are inverses and we do a composition? So f and g here are inverse functions. If we compose two functions that are inverses, you just get x out. So what that's going to look like for these two, e to the natural log x just equals x. Or the other way, natural log of e to the x just equals x. Okay, whichever way you do your composition. Okay, so more on that in 12.6 when we start solving equations.